An attosecond. How much is this compared to a second? It's pretty short. But what is time after all? Hi, I'm Axel. I'm a researcher at ETH Zürich working in the field of atom science. Usually I develop the exact electron factorization, which is a single electron theory that can describe many electron phenomena. However, that's not what I'm going to talk about today. Instead, I'm going to talk about how time appears in quantum mechanics. So, how does time work in quantum mechanics? We have a quantum system, we interact with it, and we measure how it changes. To do so, we compare this quantum system to another system, which I call the clock, and which provides some control parameter that you may call the time. Now, the concept of a clock in this respect is a rather general one. In atom science, it's a laser field, but it can also be a different physical system. If our quantum system of interest is everything, that is, the whole universe, then you immediately see that there can be no time, because there is nothing else to compare to. So time is an internal and relational concept that has to be derived from a timeless description. The equation describing a closed quantum system of energy E is the Schrodinger equation. Now, the Hamiltonian appearing in this equation is a sum of the Hamiltonian for the system, one for the clock, and one which describes the interaction between the system and the clock. Now, the absolute square of this state function for the total system is the joint probability density. And we can write it as a product of a marginal probability density, which depends only on the clock, and a probability density for the system which conditionally depends on the clock. This ansatz is what is called the exact factorization, and it essentially introduces conditional probabilities into the state function of the quantum system. And we will now see how it will help us to derive time in quantum mechanics. From the exact factorization, we get an equation for the system which looks like this. On the left-hand side, you have an operator, I call it C, which depends explicitly on the state function of the clock. On the right-hand side, you have the Hamiltonian for your system, and some additional terms which I just call U. Now, in practice, if you select a clock, you select it such that it is well described by a classical theory, so that it has a well described position and momentum. And you can use this to define a parameter t, which is units of time, and which you can just call the time. Now, to do this formally here, you have to take the classical limit for this state function of the clock. And if you do this, you will see that the U operator completely disappears, while the C hat operator essentially becomes a time derivative. Now, this equation down here is the well-known time-dependent Schrodinger equation, or TDSE. And how do we call this equation? Well, the central difference between this equation and this one is that here we compare to a classical external time parameter, while here we compare to a clock, which is still described quantum mechanically. That's why I usually call this equation the clock-dependent Schrodinger equation, or CDSE. Now, the clock-dependent Schrodinger equation can exactly be used like its time-dependent analog. However, it is also mathematically much more complicated. And if you want to understand experiments probing the quantum world, you typically need this kind of classical parameters. So the TDSE is much more useful than the CDSE in general. However, there are some reasons why the CDSE can be potentially very useful, but this video is not the place where we are going to talk about it. From our short discussion, we learned that time is not measured directly, but that what is actually measured is the clock. That time is an internal and relational concept, which we learned even without invoking the theory of relativity. that the time-dependent Schrodinger equation, the famous equation of quantum mechanics, is actually a semi-classical theory, and that there is a fully quantum mechanical analogon, which is called the clock-dependent Schrodinger equation. Now I guess that's something to think about.